This is a chem study film for use in the Chemical Education Material Study course in chemistry.
Molecular vibrations are often studied experimentally with the aid of the infrared spectrophotometer. The molecules of a gas in an absorption cell will absorb certain frequencies from an infrared beam, depending upon their particular structures and modes of vibration. Let us examine a random mixture of gas molecules to gain a better understanding of their movements and structures. In slow motion, we can see that all these molecules have translational motion. Molecules containing more than one atom can also rotate and vibrate. In this film, we consider only vibration, movement which changes the internuclear distances. Sometimes vibration is simple in form, as in this diatomic molecule. Sometimes, as in this formamide molecule, it is complex. But what appears here to be a general vibration can be resolved into simpler, basic vibrational patterns, which are known as the fundamental or normal modes of vibration. Observing closely some of the normal modes of vibration of the formamide molecule, we can see that each vibrational mode has a different frequency, and all of the patterns of vibration may be different. Each of the vibrations is a simple harmonic motion, and all of the atoms executing this motion are moving in phase, passing through their center or equilibrium positions at the same instant. The number of possible modes of vibration a molecule may have is determined by the number of atoms it has. And for nonlinear molecules, it is 3 times the number of atoms less 6. Let's see how this result is derived. First, in order to get the location of an atom in space, it is necessary to specify its 3 coordinates. If n represents the number of atoms in a molecule, it follows that a total of 3 times n coordinates are required to specify the positions of all the atoms. There are many ways of designating these positions in space. For our purposes, however, we choose a particular set of linear and angular coordinates. First, 3 of these 3n coordinates are used to locate the position of the center of mass of the molecule. Next, we require 3 angles to specify the orientation of any nonlinear molecule. 1, 2, 3. Thus, 6 coordinates are needed to establish both the position and orientation of the molecule. 1, 2, 3, 4, 5, 6. Since we know it takes a total of 3n coordinates to specify the positions of all its atoms, the remaining coordinates, therefore, locate each atom with respect to the others in the molecule. One such set of internal coordinates in the water molecule includes the 2 hydrogen-oxygen bond lengths and the angle between them. Now, the positions and orientation of the molecule, as well as the relative positions of the atoms within the molecule, are continually changing. The total motion may be described in terms of these 3n coordinates, while the internal motion or vibration alone is specified by these 3n minus 6 coordinates. It is possible to find a set of 3n-6 coordinates such that the complex vibrational motions may be resolved into 3n-6 simple harmonic motions called normal modes of vibration. Therefore, in all nonlinear molecules, there are 3n-6 normal modes of vibration. Since the water molecule contains 3 atoms, it has 3 normal modes of vibration: an asymmetric stretching motion, another motion which is symmetric stretching and partly bending of the molecular bond, and a third motion which is mostly bending. The frequency of each of these modes of vibration is determined by the masses of the nuclei of the atoms and the strength of the bonds between them. In heavy water, for example, the frequencies are lower because the deuterium atoms have greater mass than the hydrogen atoms. For any linear molecule, such as this one of carbon dioxide, the formula for the number of normal modes becomes 3n-5, because only 2 angles are necessary to specify its orientation in space. 1, 2. The third angle is unnecessary because neither infrared light nor ordinary collisions impart any rotation around the long axis of a linear molecule. This means that the vibrations of carbon dioxide can be resolved into 4 normal modes: 2 stretching modes, a mode which is asymmetric and a mode which is symmetric, and 2 bending modes, which have the same frequencies because the same bond strengths and atomic masses are involved. Vibrational modes which do have the same frequency are said to be degenerate. Let's view them from head on. The degenerate modes combine to make a single motion. In this head-on view, the motion appears elliptical. Next, let us examine methane, which has 5 atoms, to determine its modes of vibration. According to the formula, its vibrations can be resolved into 9 normal modes. One mode is this totally symmetrical stretching mode, also called breathing mode. When we examine its next 2 modes of vibration, we find that because of the symmetry of methane, their frequencies are the same. The result is a doubly degenerate bending vibration. When we look at the next 3 modes, we find that since the masses and forces are identical, these modes combine to give a triply degenerate vibration. This is the asymmetric stretching vibration of methane. The remaining 3 modes are also triply degenerate. This is the triply degenerate bending vibration of methane. So we see that though methane vibrations can be resolved into 9 normal modes, there are only 4 frequencies of vibration that are different. Therefore, methane is a good example of a degenerate system. A mode of vibration may take on different amplitudes depending on the amount of energy in the molecule. The movement of this carbon monoxide molecule represents its vibration in its lowest energy state. By collisions, this carbon monoxide molecule can be raised to states of higher energy which have the same frequency but greater amplitudes. By the same means, a molecule can drop back to lower energy states. The same thing can occur through the action of light, by absorption or by emission. In a polyatomic molecule, water for example, its several vibrational modes may be individually excited or excited in any combination with one another. In any molecule, the amplitude of vibration increases and also decreases by distinct jumps, because vibrational energy is gained or lost only by definite quanta. Therefore, a molecule can possess only certain discrete levels of energy. When a molecule absorbs energy to increase its vibrational level, it generally absorbs light of the same frequency as one of its normal modes. So, by measuring the frequencies of light absorbed, the frequencies of its several normal modes of vibration are measured. From these vibrations, we derive information regarding energy levels and strengths of chemical bonds. Certain vibrational frequencies are characteristic of certain chemical bonds and serve to reveal their presence in complex molecules. Raman spectra, nuclear magnetic resonance, and microwaves also reveal the details of molecular structure, but clues to the structure of many important compounds, penicillin for example, have been furnished by the infrared measurement of their molecular vibrations.